This video will discuss what camera shutter latency is, what problems it causes, and ways to resolve those issues. Camera shutter latency is when there are delays in software or hardware that causes a difference between what is in the image header for the start time and when the actual exposure started. In this illustrated example, when the laptop starts the exposure, the software takes a timestamp and then sends a command to the camera to tell it to start the exposure. During this process, there can be unknown delays in the computer, command transmission, and a delay in the camera itself before the exposure truly starts. Depending on the system, the latency could be 1/10 of a second or even longer than a second. In this illustrated example, the delay is 338 milliseconds. This delay may change whenever there is a change in the hardware or software. Even if the laptop's clock is very accurate, that alone is not accounting for the delays in the whole system for the exposure to start. 388 milliseconds may seem small, but there are several cases where this delay can be very important if not taken into account. Fast near-Earth objects and low Earth orbit satellites. Both travel quickly across the sky. If their position is recorded at the wrong time, it can greatly affect finding their true orbit. Occultations. Where an asteroid or other object passes in front of a star requires precise timing. The time of when it goes in front of and passes the star is very important. A measurement that is off can greatly affect the usefulness of the observation. Anything where strict timing is important, camera latency could cause an issue. Now that we know what camera latency is, you may wonder what can be done about it. You can use a camera with a GPS receiver integrated into it. When using the correct image acquisition software, the software can get the real exposure start time from the camera itself. The camera has a clock that synchronizes with location satellites like GPS, and it records when it truly starts the exposure. This, however, limits you to particular cameras, as well as particular acquisition software. Another method to find the shutter latency is by doing astrometry on well-known position satellites like GPS. You record the GPS satellite and their position, then obtain the time offset from what the real time should have been. There is a limit of how accurate you can get with this method, and it may take away from valuable dark sky time anytime you need to find the latency after a change. The main method this video will cover from here on is about NEXTA, or New Exposure Timing Analyzer. The paper Reaching Sub-Millisecond Accuracy in Stellar Occultations and Artificial Satellites Tracking is a paper that explains a method you can build your own device to measure the shutter latency of your setup. NEXTA uses a set of blinking LEDs time synchronized with navigation satellites. The pattern of LEDs shows the time. We started a project that has software to automatically calculate the time from the NEXTA LED patterns and gives you the offset, as well as row read time in rolling shutter cameras. After having this offset, you can adjust your start time in your image headers. The following is a quick demonstration of an example of using NEXTA to get the shutter latency. First, take the computer, camera, and cables as close to your real setup as you can, using the same software, and put a lens on the camera so that you can image the NEXTA board. Make sure the board is focused. Make sure everything is secure so it does not move. First, take a longer exposure with the lights on so it picks up the LEDs when it is powered off. Then power it on, making sure not to bump or move anything. It can take up to 20 minutes for complete time synchronization to occur. Once it is synchronized, turn off any lights and take the shortest exposure you can with the camera. Take your captured images into the NEXTA analysis software. Begin by opening the image captured with the lights on to allow for LED registration. In this video, we demonstrate an automated registration process. However, if it fails, you have the option to manually register the LEDs. After we have the registration, we can load our short exposure and analyze it to get the true time. Notice the line patterns on some of the LEDs. This is from using a rolling shutter camera. From these patterns, we can calculate the row reading time, which is shown in the table on the right. Thank you for watching this video about camera shutter latency.